We continue with analog indicating instruments in lecture 3. Let us recap what we learned in the last lecture. We learned that the measuring instruments are of two different classes. One is the direct reading instruments, which we are all very familiar with, and the other one is the comparison type of instruments. Some comparisons are also direct reading, like the scale. When I use the scale, I compare the scale length with the length that I want to measure and make a measurement directly. On the other hand, if I use a balance, right, then it is an iterative step. I will have to approximate the known weight or the substance to balance the known weight and hence make a measurement. And we looked at the direct reading instrument, and the first instrument that we learned in the last class is the permanent magnet moving coil instrument. It also happens to be the very first electrical measuring instrument that was developed. The principle is very simple. We use the force that would be exerted on a conductor carrying current in a magnetic field. This force is known as the magnetic Lorentz force. And in the last class we looked at the PMMC meter in detail. The meter houses a coil in an annular space created by two pole pieces and a central cylinder, and the pole pieces are energized magnetically using a permanent magnet, and the arrangement is such that the angle subtended by the coil carrying the current and the magnetic field is always 90 degrees, so that in the Lorentz force BLI sin theta, right, theta becomes 90 degrees, sin 90 is 1, so we have BLI, and we derived that the deflection angle theta is a constant time the current through the coil. The constant is dictated by the flux in the annular space, flux density in the annular space, the area of interaction of the coil with the magnetic field, number of turns in the coil divided by the spring constant, that the constant of the springs that restrain the coil from running away, right. And in the last class we saw that if the direction of the current is reversed, theta also will be reversed. If for a particular direction theta is in the clockwise direction, if I reverse the current it will be in the anti-clockwise direction. So obviously if I give an AC signal, right, alternating current signal, which alternates between positive current and negative current, theta would become positive and negative and the pointer would oscillate, right. So invariably we say the PMMC meter is not suitable for AC and it is suitable for DC and also particular polarity, because the way that we construct the meter becomes polarized, so I can measure only current in a particular direction. If I reverse the current, the pointer will kick back and it will not show any reading on the scale. We also looked at the PMMC meter as an electromechanical system, and we understood that because it has a moment of inertia, the spring and the viscous damping which is created by air as well as the magnetic induction, the system behaves like a second order system, and a second order, typical second order system we characterized by the natural frequency and the damping factor, right. Depending upon the damping factor, the transient response of the system will be dictated. We saw that if it is over damped, then the system takes a long time to stabilize and show a value. If it is critically damped, of course it is the optimal time, but it is under damped, the system goes for an initial oscillation and settles down, right. And most of the manufacturers want the meter to read as quickly as possible, so they would make the system slightly under damped, so that the meter just overshoots a little but settles down very quickly, right. Um, so in this we talked about the time for the meter to give me the correct reading, right. This time we know is called the settling time. So settling time we normally indicate the variable tau s is the time required for the meter to indicate the final value, and those of us who already have a knowledge on second order systems, this final value can be reached only at time t equal to infinity, right. But all practical purposes after some time the difference between the final value and the value indicated is so small that we can say that it has reached final value. So whenever I talk about settling time, I also have to say how much is the closeness that I can tolerate, right, because I can't wait for infinite. So I can say that the meter goes to nearly this value that it has to indicate within certain percentage, x percentage, right. Say within plus or minus 3% of the settling value, it takes 1.2 seconds, that is one value. Standardization is always there. So if I do not use any percentage, if I simply say settling time is 1 second, it automatically means that the plus or minus percent is 1%. So this is the standard value. If you are indicating anything other than that, okay. Now we also looked at the meter as a system that would have a dynamic behavior. When I say dynamic behavior, the input becomes a sine wave, right. So if I look at the system, a second order system, if I vary the frequency given, obviously it does not make sense for a PMMC meter, right, because PMMC meter we have already decided it is no good for AC, because in the whenever current becomes negative, the deflection becomes the other direction, and either we have to put a center zero pointer, right. Normally we do not do that, right, very rarely we have a center zero meter for specific reasons, but most of the PMMC meters will start with 0 and anything negative we cannot measure, right. So but if I look at it as a system, then it will have a low pass function with a cutoff frequency omega c radians per second, right. Because it is a physical mechanical system with springs and coils and the rotating arrangement, the omega c would be very very small, right. Maybe in the range of 10 radians per second, right. People have done quite a lot of research to increase this omega c at one point of a time long back, right, and the best they could get was something around 150 to 200 radians per second, right. Generally this would be less than 10 radians per second, which means the cutoff frequency would be roughly somewhere around 1 to 2 hertz, right. So if I look at this in frequency domain, so if I put this as f, then this will be about 2 hertz, less than 2 hertz. So this is another reason we keep saying that the PMMC meter is a DC meter, because even if I want to make it as an AC meter, the mechanical system natural frequency is small and I cannot measure even 50 hertz, right. Definitely I cannot measure in terms of kilohertz, right. So it is a DC meter. Now if I say that it will respond only less than 2 hertz and it will respond only to DC, right, and we know from Fourier series expansion, if I have a function f of t, we have a repetitive function f of t in terms of Fourier series, right, a naught plus sigma n is equal to 1 to infinity a n cos n omega t plus b n sin n omega t, right. And in that a naught is the constant component, a naught we also call the DC component in my function, and a naught I can write it as 1 by t integral 0 to t f of t dt, right. So now we are going to link these two. My PMMC meter would respond only to very low frequencies, and I can get a stable reading only if I send a DC current. Now the DC value of any function is the average value of the function, 1 by t integral 0 to t f of t is nothing but the average value of the function. So indirectly now I can say a PMMC meter reads the average value, right. The PMMC reads the average value because the mechanical system cannot, on the mechanical side it cannot respond to higher frequencies, right. It does not actually compute average, right. It responds to DC and DC happens to be the average of any given function, right. Now if we want to make a PMMC meter, then what are all the things that we will have to look at? The first thing is of course the coil, right. The heart of the system is a coil through which we send the current. If we look at the expression, theta is equal to B A N by Ks into I, right, and so if I look at this, the number of turns in the coil influences the theta that I can get, right. So I would like to have many number of turns as possible, right, so that my Km is large, but I can't have physically 1000 turns, right. 1000 turns will be really a big bulky coil, so there is a physical limitation of number of turns, right. 20, 30, 100, that is a maximum we can do, and if I want to put large number of turns I will also have to make the coil as thin as possible, that is not a problem, but a very thin coil is very easy to break, right. So again I cannot go below certain thickness. The area of cross section of the coil is again a design factor, right. The area of cross section would have to be small, otherwise if I put such a big coil then my meter will be very large, right. I want to have the meter very portable, small, so area would be few centimeter square, that is the best I can. The spring constant has to be small for my Km to be large, right, because it comes in the denominator, again there is a limitation. I cannot keep the spring thinner and thinner, then I cannot make the spring work for a long time. The flux density B must be as large as possible. This again depends upon the permanent magnet. The permanent magnet that we employ will have certain maximum flux density that it can produce. Now if we really look at the permanent magnet, people initially used permanent magnet of a particular type, which was a composite magnet made out of aluminum, nickel, cobalt and some amount of copper and titanium, right. So the table I have given here provides different types of magnets, Alnico magnets, right. And one thing that we have to really look at is the remnant flux in Tesla. The remnant flux, higher the remnant flux, higher the air flux that I will get, that will interact with the coil, right. The second thing that is very important is the coercive field intensity. Higher the coercive field intensity, the magnet would last long, right. And so these type of magnets were initially used. Later, after about 50-60 years of Alnico's realm, then came another type of magnets, right. Called Ferrox-Dürr. The Ferrox-Dürr magnet is again a composite magnet. Most of you would have seen it. If you look at a loudspeaker, you see a big black magnet at the back, that is Ferrox-Dürr. Compared to Alnico, Ferrox-Dürr is very easy to make and also it is very cheap, right. But most of the meter application, when it came to PMMC, Alnico was used, right. Now if you look at the other parameters that we will have to look at if you want to make a PMMC meter, the pivots and the springs, they go hand in hand. Initially the pivots were what is known as a pin and socket. There is a socket, there is a socket there is a socket on top of it and I have a pin that rotates in that, right. That is what I have shown it in the but this is not very good, because as the meter goes through usage, the pin grinds the socket and then it becomes very sticky or very loose and you will have all sorts of problems, right. Later there was a development parallelly taking place in another area, the wristwatches, right. So the wristwatches in the earlier days had the same spring arrangements for clocking mechanism, and then there were two wheels rotating and they have to be pivoted, right, and those also used pin and socket, right. And after a while, in 1902 a discovery was made that instead of using pin and socket, a jewel bearing can be used for the wristwatches. Actually this jewel bearing was not developed for PMMC instrument, it was developed for watches, right. If you look at old watches, then the manufacturer would say 21 jewels, 17 jewels, right. The name jewel was given because these bearings were made actually with precious stones like ruby, emerald, right, and they were used in jewels, so they call this jewel bearing. For example, if I put let us say steel on steel, the friction coefficient I will get is about 0.6. If I put steel on emerald or ruby, right, hard stone, then the friction coefficient becomes 0.15, which means it is going to be very smooth, it is not going to rub, the friction is very small, and my sensitivity would be can be adjusted to be large, right. And initially they actually used precious stones, then somebody came up with a mechanism of producing artificial gems, right. So these are artificial ruby, there is no difference between natural and the artificial one, except this is man made, right. And later people also looked at how to increase the sensitivity. You can't keep on reducing the thinness of the spring, because the spring is no longer practically possible to make. Then they simply put two rubber bands, one on top, one at the bottom, right, stretch the rubber band and held the coil, right. So this will be flat rubber bands, and the rubber band will get twisted and it will come back to normal. These are called taut band suspensions, right, and the taut band suspensions were very fragile in nature. You keep the meter with the kind of acceleration, right, and the taut band will break. So you will have to take care if it is a taut band suspension meter. So the once we make a meter, right, the meter theta is determined, right. So I may have my pointer going from theta equal to 0 to theta equal to theta full scale, and I have my current through the coil is 0 to current through the coil as I full scale, right. And because the relationship between theta and the current is linear, I can now put the graduation, right. I can say exactly when theta is equal to theta full scale by 2, I will have I is equal to I full scale by 2, right. I will have I equal to I full scale by 2. So for example, if I make theta full scale to be 100 degrees, right, and then I make I full scale is equal to 100 microamperes. These are actually practical values, right. Then 50 degrees would be 50 microamperes, 51 degrees will be 51 microamperes, and so on. So I can now mark every degree. So I put 1 degree, this will be 1 microampere, right. So now I have 1 degree is equal to 1 microampere, and my full scale is 100 degree is equal to 100 microampere, right. So if I mark the scale in 1 degrees, my resolution becomes 1 microampere. The least value I can read would be 1 microampere. So my resolution is one degree, which is equal to 1 microamperes, or I can also say 1 by 100. 1 microampere is the resolution, 100 microampere is full scale. So I can say it as a ratio of 1 in 100, resolution is 1 by 100. So basically a PMMC meter is an ammeter, right, of full scale value whatever we design. Now when we design, let us say this particular design, I put 100 microamperes, 100 degrees, I have put the scale, I have put pointer, everything, and when the manufacturer starts making these meters, he will be using different permanent magnets, right, from the production line for different meters. First meter, one magnet he will put, second meter he will put, but these magnets, however hard you try, when you manufacture let us say 1000 magnets, each one will have a different value of flux density, right, remnant flux density. One may have 0.76 Tesla, the other one could go down to 0.7 Tesla, this third one could be 0.85 Tesla, and so on. So there would be a variation. So my B he is going to change some B average plus or minus B deviation, right. Coil I can make it perfect. When I say I am going to put 50 turns in my coil, I can count exactly 50 turns, I cannot make any mistakes. If I want to make it exactly 5 centimeter square, I can make it 5 centimeter square. So A and N will not be a problem, but Ks again would be a problem. When I make springs, Ks again would have some average value, Ks average value plus some deviation, right. So in fact, when you want to buy springs from the manufacturer would give a Ks of so many nano Newton per meter as my as the spring constant, and then you will say the best I can do is plus or minus 10%, which means if it is 100 nano Newton per meter, then you can get springs from 90 to 110, whatever is possible. So when he makes the meter, obviously he has to make such that whatever be the permutation combinations of the magnet and the spring that he chooses to put in that particular meter, it should be possible for him to adjust 100 microampere to give 100 degrees. So the method that the manufacturer adopts is very simple, right. If you really look at the meter, right, the flux, there is a main flux phi, I call this phi for the meter, right. Then the manufacturer produces an auxiliary flux through a second branch, this I call it as phi shunt branch, right. Just put a wedge type of right, something like this, bridging the air gap, right. By adjusting this wedge, right, forward and reverse, the manufacturer can adjust the shunt flux, right. So he would calculate what would be the constant that is required for the worst case. Worst case is highest value of Ks and lowest value of B, right. For that, if he can adjust full scale 100 microampere to 100 degree centigrade, any other value he can simply alter the shunt field, right, and reduce B to compensate for change in B as well as compensate in changes for in the spring constant, right. So if you open your PMMC meter, you will find this adjustment screw here, one screw, right. Please do not touch, because the manufacturer adjusted the shunt wedge so that you get 100 microampere to. Now the initially the manufacturer will set all the parameters and the pointer would point at 0, right. As you start using it, maybe 1 year, 2 year, the spring would have gone through several wind unwind cycle, and then what will happen to the spring? It may become a little loose, right. So even though you have not sent any current, the pointer would either be less than 0 or more than 0, right. So the pointer would have shifted, we call this as a drift, right, drift due to time and usage, and all you need to do is tighten the spring a little or loosen a spring little, so that the pointer goes back to 0, right. So for that, most of the manufacturers gives you a small screw at the top of the meter called zero adjustment. When you tighten or loosen the screw the spring is tightened or loosened, so that the pointer goes back to 0 in the initial condition. So there would be a 0 adjustment which the user can use, there will be a full scale adjustment normally impervious to the user, which is inside the meter. The manufacturer, or if you want to calibrate the instrument, if you go to a calibration lab, the calibration lab will adjust this shunt flux to get 100 microampere read 100 degrees, right. It need not be 100 microampere to 100 degrees, it could be 60 degrees for 100 microamperes, right, whatever is the full scale. I chose 100 microampere for 100 degrees because easy to do, right. So if I look at in the overall meter, I have an ammeter, that is a PMMC meter, the meter is made of a coil. So obviously I have a resistance of the coil and the inductance of the coil. So this would be the basic meter, right. So when I send a current, I have the full scale current. Because it is DC, I do not have to worry about inductance, because we know inductance for DC is a short circuit, 0 impedance. So there would be a voltage that would be developed across the meter, we call it as V full scale, right. Okay. For example, in this particular case, the resistance of the coil is, let us say, 10 ohms, and 100 microampere is my full scale. So V full scale, I full scale is 100 microamperes, and V full scale would be 10 into 100 microamperes will be 1 milliampere, 1 millivolt, right. So you would see manufacturers giving you the specification saying that my meter is 100 microampere stroke 1 millivolt PMMC meter, right. What does it mean? The meter has 100 microampere full scale, and when I send 100 microampere full scale current through the meter, the drop across the meter is 1 millivolt, right. So the moment I have a basic ammeter, it is possible for me to design and get any other full scale, right. Let us say I want to get not 100 microamperes, I want another ammeter, and I want that ammeter to be 100 milliampere. So now I have I am omitting the inductance, we are talking about only DC currents, right. So inductance does not come into picture when I use DC, okay. So I am omitting the DC current. So I have the coil resistance of the basic ammeter. So I full scale is equal to 100 microamperes, and V full scale is equal to 1 millivolt, that is what we decided. Now I want to convert this into a full scale of 1 milliampere. Now I want I full scale dash to be 1 milliampere. All I need to do is put a shunt resistor across the meter, so that when I send 1 milliampere, 100 microampere flows through the meter and 900 microamperes flows through the shunt, right. Okay. So now I know at full scale current of 1 milliampere, full scale voltage is 1 millivolt across the shunt. So, R shunt is equal to V full scale divided by 900 microamperes, which is 1000 microamperes divided by 900 microvolts divided by 900 microamperes. So, I can cancel this. So, this will be 10 by 9, which is 1.11 ohms. So, if I connect a 1.11 ohm across the 100 microampere 1 millivolt full scale PMMC ammeter, the resulting ammeter becomes a 1 milliampere full scale. If I give 1 milliampere full scale, 900 microamperes will go through the shunt, 100 microampere will go through the meter, and I will have 100-degree deflection. I will read full scale. Now, if I give 0.5 milliampere here, because it is only resistive division, right, 450 microamperes will flow through the shunt resistor and 50 microampere would flow through the meter, and my meter will show half. So, I know it is 0.5 milliampere. So, the same 100 divisions I can now remark as 1 milliampere, 0.5 milliamperes, and all the other values. I can put several shunts like this, right. I can put another shunt, a second shunt, and I can put a switch here, right, and I choose RSH1 so that it is 1 milliampere and RSH2 so that when I connect it here, then the full scale can be 10 milliamperes or 1 ampere, right. I can choose depending upon the requirement, right, my requirement. I can even choose a 10 ampere full scale meter, and I can also make multiple range ammeters. I can put a switch and make, if I put a particular switch, it is 100 microamperes, nothing is connected across it. I put it in position 1, I put a shunt resistance of 1.11 ohms, it becomes 1 milliampere full scale. I can put another position which becomes 100 milliamperes full scale. So, I can also make multiple range ammeters, right. And please note, I can only make the range higher than the original range. If I have a 100 microampere full scale PMMC meter, can I get a 50 microampere full scale? I cannot, whereas I can get 200 microamperes, I can get 2 amperes, 10 amperes. The limiting factor would be the physical value and the size of the shunt, right. I can't put 1000 amperes. Why can't I put 1000 amperes? I want to put a shunt resistance so that the current becomes 1000 amperes full scale current. Let us do that. At 1000 amperes, my meter current should still be 100 microamperes. So, my shunt current must be, right, my shunt current must be 999.9 am I right, 9 ampere, right, 100 microamperes flows through my meter. Okay. Now, if I look at the shunt value is 1000 microvolts divided by 999.9999 ampere. How much it is going to be? It is approximately 1000 microvolts by 1000 amperes, right. I can say approximately 1 micro ohm. Making a 1 micro ohm shunt resistance is practically very difficult. Even if I make one, when I connect this shunt here, the contact resistance itself will be few hundred micro ohms, right. Even assume that I can make 1 micro ohms, right, I cannot ensure when I connect it, the contact resistance of my connection would be few hundred micro ohms, the best I can get, right. And the second thing is, what happens to the power dissipated in the resistor? Power is, all of us know, is I square R, right. So I square would be approximately 1000, 10 power 6. So the power in the shunt, resistance would be 10 power 6 into 10 power minus 6, right. This is 1 micro ohms, right. So I square R would be 1 watt, right, and 1 watt is the power that would heat up the meter, right. The meter would become warm, right. How many of you have actually looked at a 1 watt resistor dissipating 1 watt? It will be warm, right. Okay. So there are practical limitations for putting this shunt. Generally up to 10 amperes, 20-25 amperes you can put shunt. After that you cannot really put a shunt and get a 100 ampere full scale meter, very difficult, right. And the shunts, connection of shunts, everything becomes really a big problem. Now we have the 100 microamperes and this is 10 ohms. So this is 1 millivolt, right, full scale. Now I can connect a series resistance, right, of value, and when I apply a full scale voltage, the full scale current of 100 microampere flows through it, right. Let us say my full scale I want voltage, I want is 1 volt, right. So when I apply 1 volt, I must get 100 microamperes. So the total resistance must be 1 volt divided by 100 microampere, that would be 1000 millivolts by 0.1 milliampere, it is 10 kilo ohms, right. So if the total resistance is 10 kilo ohms, if I apply 1 volt, I will get 100 microamperes flowing in this circuit. Now I already have 10 ohms, so I make this as 9990 ohms, right. Once I connect like this, I apply 1 volt, I will get 100 microamperes, my pointer would deflect full scale. Now I apply 0.5 volts, 0.5 volts divided by 10 kilo ohms would be 50 microamperes and the pointer will reflect half. So the same meter scale now becomes 0 to 1 volt indicating. So by connecting a shunt resistance, I can convert my basic PMMC ammeter into any type of ammeter I want, any full scale amperage I want. By connecting a series resistance to my basic PMMC ammeter, I can convert the ammeter into a voltmeter, right, simply connecting a series resistance. And if I look at an ideal voltmeter and an ideal ammeter, because I am going to put in my circuit, let us say this is my voltage source, this is my resistance, we are talking about DC, so only resistance, I am not including the impedance here, right, and the ammeter should not disturb the circuit because I am measuring the current. So for an ideal ammeter, the meter resistance must be 0. If I want to measure a voltage, I put a voltmeter across the resistor, right, and when I connect the voltmeter across the resistor, it should not disturb the circuit. So which means the voltmeter should not take any current, right, it has a voltage but no current, IV must be 0. So our voltmeter must be infinity, So, for an ideal ammeter, its internal resistance must be 0, an ideal voltmeter, its internal resistance must be infinity. Now, in both cases, when I looked at as an ammeter or as a voltmeter, the PMMC meter is not an ideal meter, right. It has certain resistance when it is an ammeter, right, non-zero resistance, and again it is certain resistance when it is a voltmeter, not infinity, right. So, it is not an ideal voltmeter. So, how do I specify that, okay, there is a non-ideality, it is not an ideal ammeter, it is not an ideal voltmeter. People earlier in the earlier years have come up with a specification called figure of merit. Right. The figure of merit for an ammeter or a voltmeter, it is independent of whether what type of meter it is, right, is given in terms of 1 by I full scale current, right. Okay. So, it is 1 by I full scale. For some reason they did not want to put it as ampere inverse, the unit, they assume that the numerator is 1 volt, right, and I multiply denominator also by 1 volt. What is this now? Figure of merit is 1 by I full scale, right. I am artificially multiplying numerator and denominator by 1 volt, right. So, this I know is volt by current is ohms. So, now I can write this as ohms per volt, volt is already there, this is not cancelled, right. So, figure of merit of a meter is given in terms of ohms per volt, right, always given in terms of ohms per volt, whether it is immaterial whether I am using it as an ammeter or as a voltmeter, right. It becomes more and more important when we talk about in the context of voltmeters, right. So, higher the ohms per volt is rather small. So, most of the figure of merit that you would get in a meter would be kilo ohms per volt. For example, what is the 100 microamperes figure of merit? 1 by 100 microampere, which is 10 kilo ohm per volt. So, the figure of merit for this meter is 10 kilo ohm per volt. So, figure of merit is always given in kilo ohms per volt, even though unit is ohms, right. We stop here, we will continue in the next class.